So, I will be talking about Mistune bladed disc vibration problems, an important issue in aerospace and mechanical engineering. A bladed disc or bliss is a key rotating component found in jet engines and gas turbines. It consists of a central disc with multiple blades attached around its edge. As this component spins at extremely high speeds, it becomes highly sensitive to vibration. In an ideal world, all blades will be perfectly identical, but in reality, due to tiny manufacturing imperfection or material inconsistencies, each blade may behave slightly differently. This small variation is called mistuning. Mistuning might sound minor, but it can lead to serious problems. One of the main issues is something called mode localization, where vibration energy becomes concentrated on just a few blades instead of being evenly distributed. This causes those blades to experience much higher stress than expected, which can eventually lead to fatigue, cracks, or even catastrophic failure. To predict and prevent these failures, engineers use a technique called eigenvalue sensitivity analysis. This mathematical approach based on solving differential equations allows us to understand how small change in blade properties affect the vibration behavior of the whole system. By using this analysis early in the design stage, we can optimize the bliss structure, reduce maintenance costs, and improve engine reliability.
So now let's start by imagining a simple mathematical system. Picture a bladed disc like the ones you might see in the jet engine, with just two blades that are connected in the central hub. Now, each blade behave like a spring mass system. When the engine runs, these blades vibrate, but there's a catch. Because of something called mistuning, which means slight differences in properties like stiffness, the blades don't vibrate exactly the same way. To understand this behavior, we model the systems as two meshes, represent the x1t and x2t, which describe how each blade moves over time. We also have a stiffness matrix that includes K1 and K2, the stiffness of each blade, and they might slightly different due to mistuning. Kc, the coupling stiffness, which is how tightly the blades interact with each other. M, the mass of each blade. The metric equation have represent how all these forces interact. It's essentially Newton's second law for this vibrating system. Force equal mass times acceleration. To solve this system, we assume the motion is harmonic, like a sine wave. So we use a standard form, which the first equation. When we plug this into a matrix equation, we get what's known as eigenvalue problem. Basically, we're trying to find value of angular frequency and P mode shape that satisfy this equation. This amplified to the familiar form AP equal to lambda P, where lambda is eigenvalue frequency W square. Solving this gives us a natural frequencies and vibration modes of the system, and that's how we can analyze how mistuning affects blade vibration. Now let's briefly define our system. Let's plug in some examples value to see how this works in practice. We let the mass M be 1 and the coupling stiffness K be 1. In the tune case, both blades have equal stiffness, K1 equal to K2 equal to 2. In the mistune case, blade 2 is stiffer, so K2 is 3, while K1 stay the same. From this, we put the stiffness matrix K. For the tune case, the matrix becomes K equal to 3 minus 1 minus 1 and 3. This matrix includes the interaction between the blades and the coupling. To analyze the system's behavior, we solve this characteristic equation determining K minus lambda I equal to 0. This gives us eigenvalues lambda equal to 2 and 4. And since eigenvalues represent W2, the square roots of this value give us a natural frequency where W equal to set 2 and 2. This frequency tells us how the blades naturally vibrate when disturbed. So, what do this result mean physically? Each eigenvalue lambda corresponds to a vibration frequency. Each eigenvector p tells us the mode shape, basically how the blades move in relation to each other during vibration. Now, here's a critical insight. If we change K2, for example, if one blade becomes stiffer due to manufacturing differences or wear, we get mistuning. This causes both the eigenvalue and eigenvector to shift. As a result, the blades vibrate in different, sometimes unpredictable ways, and that can lead to dangerous resonance and failure. So this sample model help us predict and avoid these issues, and analyzing how sensitive the system is to mistuning.
Next slide is analysis of result. Eigenvalue splitting show that different blades vibrate at different frequency. This splitting of value clearly show that each blade is no longer synchronized and vibrate on its own frequency. Blade with altered stiffness produce different mode shape. We saw that blade 1 and blade 5 with different stiffness level generate distinct vibration pattern. This support the sensitivity of the system to blade design. Last point is this help identify blade more susceptible to high vibration or failure. Using this result, we can predict which blade might experience excessive vibration and are more likely to fail over time. Next slide is on engineering impact. First point is sensitivity analysis aids in predicting and controlling mistuning effect. This type of eigenvalue sensitivity analysis allow engineers to stimulate and predict mistuning impact early in the design stage. Second point is early detection of critical vibration responses enhance engine safety and performance. By identifying dangerous vibration early, engine reliability and safety can be improved significantly.
Gas turbine blade can vibrate differently due to mistuning like manufacturing errors or material differences affecting engine performance and safety. Second, eigenvalues and eigenvectors help engineers predict and analyze this complex vibration. By method using global design variable and eigensensitivity analysis allows accurate simulation and control of mistuning effect.